you find that this works out if every time you have a process with an electron going from A to B, you must also have another process with electron. And they have to come with each other in exactly the right way that they can.
You don't see the screen. You don't see the screen.
In energy, in particle physics, we write fields in terms of.
There is no screen. You don't see screen.
They always come together in this combination. And this leads to the fact that whenever you get the process involving particles, for example, here the electron scattering into photons with a simple process that was observed very early from scattering, the existence of this process and the fact that each of these interactions, the field combined both creation and elimination, means that also we can have another process, we can emulate it. So these processes come together. So physics, I want to make this slide later. Technical. But it really has different particle physics and this particle physics.
Computer.
Okay. So in particle physics, it's a very rigid structure. Whenever you say that one process can exist, you also have all sort of cross process, which come along with it. A quick disclaimer if I start to talk. So as I mentioned, I will not try to make a Latin. Very be a conservative stop. And we go to just find out all the implications. And in practice, can developers do calculations? What extent can we test it? Or we test it? And also the particle physicists, not necessarily the atheist and so on. So I won't actually be talking about exotic metrics with spaceships going around time travel curves, so that's not what's talking about. We're going to be doing experiments in small collider in a small patch of space-time, flat neighborhood. So that's a setup.
You cannot.
So coming back to
the screen.
To the experiment. So one thing that fascinates me about this notion of causality is that something that's actually verified on vastly different length scales in nature. So at very long distances, for example, when the supernova explodes, the other side of the galaxy, we see electromagnetic radiation and neutrinos that arrive basically at the same time. Actually, neutrinos arrive a few hours earlier, but we understand that because they escape faster. So basically, the travel time is the same. And more recently, gravitational wave signals and cosmic and gamma ray signals basically arrive at the same time from very far away events. So, and what's amazing about these events is that they can occur in millions of light years. So light has traveled millions of years to reach us, and they basically arrive within seconds. It's all these different messengers are inside of each other. So the sense of nature really seems to care that about this universal speed. We can also test this principle indirectly for precision tests. So as we just seen, this principle is totally related to the fact that for every particle, you need an antiparticle with numbers. And this we can just check experiments. And we quoted the mass, charge, energy levels, tested to incredibly precise accuracy. You can also ask if
Boris, what's the point if nobody can see the screen?
We make parts and lithic parts that basically overlap with each other for a very small amount of time, or 1/4 the energy of that process. So 110 minus 27 seconds. And they behave exactly like we predict using the rules of field theory. So we see that nature really cares about all these principles and now all these extreme distances. And of course, I have to mention that sometimes experiments are more interesting.
When I was downstairs to tell them the audio wasn't working,
Some of you
see the slides then?
Enough to remember.
No slides were
There's a
never.
great shock when we on neutrinos were measured in 2011 provide
Slides, but
flexible
obviously-
light.
Whoever is chatting from demo says we had issues with the speaker's computer, but they still do have them, obviously.
No, but probably it makes sense to stop to talk until they can fix it.
If it had been true, it would have been a great change in the paradigm of modern physics. It also contradicted many other experiments. So the people on this experiment, they were actually quite honest about it. They invited the community to scrutinize everything and even replicate the results. I think they had a
You don't see slides.
very commendable attitude.
Yeah,
And
no,
after
no
many
slides.
investigation, it turned out that this was
Alicia, no
a
slides.
scale that led to to synchronize, because the tough part of the experiment
Still
is to
no
synchronize
slides.
clocks using GPS system
Or
different locations.
something else. But still too small to see it.
Yeah. It's a bit funny, but at the same time,
Yeah,
this was
is
only
too
one of the
small.
weird experiments.
This is too small.
It's a great example of how, the self-correcting nature of
But better
science.
than nothing.
Eventually, you figure out. So, well, nature really seems to care about this principle, and that's basically why
This is better.
I care about understanding causality then. So, now is a little quiz for you. Let's talk about optics, because I think of waves. So we learned in classes about waves that when a wave moves in the medium, the feature of the wave moves with the group velocity. So like the little oscillations here will move with the phase velocity, which can be faster or slower. But the overall envelope, if it's a narrow band wave, will move at a group velocity. Okay, so we all familiar with that. So this. Suppose we send this wave packet into a material with the group velocity is maximum. Is that send information? Put some options in, we could then so thinking. So what happens when this thing enters the superluminal material?
Okay.
Yes. Material does not explode. And it's definitely not A. Otherwise, we'll know about lots of people getting rich. That's C. So this material actually exists. And actually, we can, if people are open for shares and papers, but what happens is that if whenever this group velocity is happening, the material shows the property that is strong activation. So basically, the overall, so they have a little but basically, the answer will stay under the tail. And so we make it at this and say, oh, it's the original button that got advanced by sigma. But in reality, what is happening is that it's this tail that got distorted. And if you cut off the signal, then you get a sharp front and there's absolutely nothing at once. So even if these materials exist, you always have you can't use them to sense in your passing. And I think this example motivates well this mathematical formula that is a general property that holds for any medium that for the dispersion relation, so n is a k of omega, is a refractive index of medium. Any medium that respects causality needs to have an index of refraction as an angle of the property, it's analyticity. And that gives a relation between its matter part, which controls absorption, and its propagation. And usually, if you don't have gain, absorption is positive, that will be positive. And if you plot this, for example, if you have a medium where you have some absorption bond at some frequency, you plug into this formula, you predict the blue curve, which is the dispersion relation, You compute this group velocity and you find that it's super low, but it's super low only when you orient. This formula only works out so that you can't like get a measurable, you can't use this faster than light group velocity to send information. So I'm actually not an expert in optics, so if there's anyone in optics that to correct me or tell me more about application of this formula, I would glad to hear. I actually came from I did my undergrad at a small university, University Laval, but there's not a lot of particle physics representation, but it's not a very good optics class that I wish I had paid more attention to. But so the reason I mentioned this is that in particle physics, a formula that's basically the same one. Dispersion relation that is not powerful too. And what we use it for is relatively the same idea. We relate process at different energies, but importantly, it relates an amplitude to something that's like the imaginary part of the amplitude, which in the context of particle physics, does not the problem relates to the production of new particles. So this allows us to reconstruct a particle scatter at some energy in terms of what particle can create a particle energy. And the physics of it is the same. It's the same number of probability. And but it has this other feature that I mentioned in the first slide, that it mixes different channels, like electron-positron annihilation, electron scattering, positron scattering, mixes all these different paths. So again, we expect that because I people mix it back. And this one is used a lot, for example, in experiments to determine the phase of the amplitude. It's also used, kind of give a talk here mentioning the famous Q-system groups. So this type of physics, this type of relation is used to relate physics that is strongly coupled at some energy range to physics that is simpler at other energy range. That's one thing you can do with that. And another thing I want to jump into this thing which is a bit more technical, which is how does this property causality relates to the energies. So spin is something that happens very naturally in particle physics also. Whenever you have a scattering process depends on some energy and some scattering. And it's very natural to analyze this process from the viewpoint of spherical objects. The extension over different spherical objects that we label by the loop, which really the spin in units. There is S waves. The claim is that normally when you do this expansion, the spin is in. Okay. The claim is that the statement that this function emits a dispersion converse from evolution is equivalent to this function being negative. So it's really so it's a restatement of an entity. So this is a relatively old idea. Let me just briefly motivate it, because I'm sure almost everyone did, I don't know. Even though in particle physics, it's not something we teach anymore. So the idea before. So if you look at the I said that it's a function of an angle. Where is an angle such that it's not like it? Somewhere still 1, 2, 3, 4, 5 converge only in this physical region. But what this spin allows you to do is to replace the sum by an angle. Then you can deform the integral and make it converge into bigger. And this bigger range gives you access to the origin. The fact that we can go from one channel to the other channel is what this NXT still means. That's right. But we also can get a physical interpretation of this real number still in that channel. It has to do with the fact that now if I look at this picture, so I just change the way. Remember in particle physics, you can look at the same diagram, but then you add 90 degrees, you change time. So if I look at this figure and time is going up, this is electron scattering. Okay. Now the state that I'm exchanging, the electron can exchange the momentum. Exchange. So the momentum exchange now is space-like. can't go to the center of mass. It's just a time-like momentum, so space-like. And the thing that, instead of being a rotation angle, the thing that describes this process with the fixed momentum transfer is the boost. So in this process, J represents not a rotation length, we go to the boost side. Boost can be arbitrary, boost can be arbitrary. Because if you boost by 2 pi, you're going to go back to this. So that's kind of a general idea for why this happens. So here's one example again from traditional old school particle physics. So one implication is that it gives you a good word for like energy scattering, meaning virtual scattering. And can parameterize exchange of expected particles. For example, proton-proton scattering. The phenomenology is very model, like exchange of expected particles scale is not considered. What this means is that this is like a boost like energy. It tells us how the cross-section changes when you increase the energy system. And name physicists. Yeah, one of that is easy. So Region gave a name to Region. Give off. Last one is Frost-Out, because I mentioned the Frost-Gribov formula in this section. So yeah, I also want to just to make this a little bit abstract. The way this is used in data is really important. So I'm saying that we have exactly states with non-integer spin that exist in nature. But what happens is that if you plot, for example, the spectrum, so on the orbital axis A, plotting the energy square and the non-energy square of extent state. When that's positive, you have energy, so that means you're talking about real particles and this integer spin. So we do logarithm, it's trajectory, some other particle that's in 3, friend that's in 5. So for time-like momenta, you just have an integer spin particles. But the claim is that if they organize into lines curve to them, and this curve you can use to predict the energy dependence of energy scattering in space-time. That's the idea. How the approach connects with external. And the other way that this formula used is that we don't just know in practice what is useful is not so much the fact that absolute analytic, but it's the fact that there's an actual formula that tells you, also legal formula, that tells you what this analytic consideration is in terms of things you can measure. That allows you to do approximations, so there are situations where you're dominated by light. There's a lot of things already, so that means maybe we talk about crossing symmetry, dispersion relation, and spin, and then you get the general message that is an all mathematical statement. So as a theorist in particle physics, trying to use the statements to influence. So next, I want to make a little detour to upgrade the conformal theories, and now these ideas apply. So far it was all ideas, and now will be some more new and interesting ones. So that's something that is actually quite remarkable. So it is a lot system, like when you boil it under relatively exotic extreme conditions of high pressure and temperature, when you approach a critical point, there's this phenomenon that the vapor becomes so dense that it's quantitatively like a liquid. But this transition becomes continuous. Boiling transition becomes continuous. And what happens, for example, is if you approach this point from there, you have a, so you start from the liquid phase. If you're very close to this point, approach from below, you will nucleate bubbles of vapor. But these phases are so close to each other, the bubble can be function. Inside the bubble of vapor will nucleate the bubble of liquid, which is also very big. This self-centered systems of bubbles inside of bubbles. So it can be, and the system develop long range correlation. Those is critical point. And very interesting thing happens there. Actually, just optically look at it. See this long range correlation. And the correlation reaches the way the things become blurry. So critical person. So you just see something neat happening. And then you can measure more quantitatively. And for example, you define a function that's 1 in one phase and 0 in the other phase, and you can correlate it with points. If you find this R here, it measures this exponent. And the exponent have very much good numbers. Okay. And the thing that surprised a lot of people back when this was for measures that you can go on, it's not first measuring digits, but still enough digits to be convincing, you can go to different systems, experiment with different gases, and you actually find many systems are controlled by the same exponents. So this phenomenon is called universality. But perspective on it, it's because these exponents have nothing to do with the infrastructure of the systems captured by the continuum theory. The continuum theory of bubbles of one type inside of bubbles of the other type. Doesn't matter what the bubbles are made of. You just have to study the continuum theory, you can calculate this. And this functional system here, actually maybe the simplest representative is Einstein theory system is filled with up down. And to get a great time model to test RS techniques, so we'll spend a few more slides on this model to explain the particle technique that is also interesting for particle physics bootstrap. So, bootstrap. So let me say a little bit more about field theories. So, something we think about those is that 3D-dimensional analysis of theory. So, saying the correlation function of some measurement, like a power law, is like saying there's a measurement that relates to this overlength. Let's accept that some quantity as this means. And then this formula makes sense, dimension-wise. And of course, if you take derivative of measurement with respect to this function, you then multiply by one length, and the units work with the unit. When you multiply measurements, but if they have different places, then in general, if they are very nearby, it says that different two nearby things, like making like some kind of composite measurements. And this formula, this kind of formula that I want you to do, it's kind of Taylor series and 2.1 side. But the funny thing with this Taylor series is that all of the exponents that the list of exponents that show up on the X also find numbers. So it's not like so compared with Taylor series, they're all numbers. But you can have the full list of these numbers in some sense if so it's Let's speak next slide. One thing I would say also is that if you take x and y to be a relatively large function, then the product works in a relatively simple way. You might expect them to be decoupled. And the sharp statement of that is that if you take two measurements, put a little derivative between them to try to make them far from each other, then actually this measurement will have approximately the scaling dimension, where the same units have a and b and the derivative up to small corrections. So, the sense that putting any derivative suppress interactions. Okay. So the bootstrap method is a method to calculate these correlation functions by looking at an object which is theoretically looks much more scary. We intercept this exponent that control correlation function of two measurements, say two scales. And the claim is that you learn about this by looking at coordinate function of 4 elements. 4 measurements at 4 different space points. But the point is we can make this expansion that I just described. So if 1 and 2 are very far from 3 and 4, as in the picture here, the first guess would be to say that they are unconnected. So one talks with 2, and 3 talks with 4, and another talks with another, and another. The extension I just described to you allows you to in terms of how the exponents. This is a thing that's called the perfect public extension. So this partial collision function, and it's this here. Okay. What's special about 4 points is that we can do this series in different ways. You start with a configuration that looks like a square, and try to understand it as a series coming from pair 1 and 2, or a series where you pair 1 and 3. That gives you 2 different series representations. We have this formula schematically. One series is equal to the other series. And called a crossing equation. And this has to be true for any position of these 4 points that you use. So it's an infinite number of constraints. And this feature is an infinite number of unknown, which is this list of exponents that appears. This was proposed by Colloquium. It had great success in 2 space dimension, but it's only relatively recently that this field has been able to make real progress in higher dimensions and discuss more realistic theories. So that's what briefly described here. And the key realization is that all the unknowns that appear in this series expansion are positive unknowns. Square of things that we 2. And because unknowns are positive, now it's no longer just a linear model. Infinitely constraints, infinitely parameters, we don't know whether there's a solution or not. It can be that there are pairs of parameters such that there is no solution. If some coefficient is forced to be negative, then you say that's not a valid solution. So we can exclude. So if you plot over parameters that interest you, like scaling dimensions, what you measure, you can turn out that if you make the wrong assumption about these parameters, you can rigorously exclude. Then you end up with exclusion class that look like this. And of course, the actual model you're not able to exclude. The good thing is that the model ends up at the boundary of what you can exclude. Then the idea is you walk over and over, and then you eat around this model. Basically, find the values of the exponent in the model you care about by excluding all the nearby options. So this program was pushed with great success in a variety of models, including models. And actually, eventually, you can include enough constraints when you have exclusion plots that give you isolate the values. And essentially, any value of the exponent outside of that little dark region are excluded. Give you a method of calculating the exponents by ruling out all other options. So if the model exists, then its exponent has to. Original way of solving those models. So, and this slide will start now we can get a little bit more analytic insights using idea of probability. The strongest statistical model was nothing about probability. 3D critical model. The trick is to, which is natural, for physicists, is to consider the 2 + 1 relation on the surface. I don't know an experimental realization of it. I would love to know one. But in this model, it's actually in the continuum model, it's actually the same as the 3D model. There's the same critical exponent, the same correlation function. You just analytically stick some eyes and some formulas, and they actually the same. It works, it's very simple to understand. If you have a system and a rotational environment, continuum model, then you stick an I in front of the coordinate and it becomes a time vector. It's an idea known as the Wick rotation. This powerful idea we can use to try to apply particle physics method to problem. And having a time direction allows you to do quantitatively different experiments. So you can do something that looks like a scattering experiment that I described earlier. We do again, it's a correlation function from all measurements, but you could imagine that this point, these 2 points here are creating some spin wave, and then you're measuring this spin wave after you pass through charge and future. So in this 2 + 1 dimensionalizing model, we can do scattering experiment of spin waves. So this model by construction respects Lorentz invariance. It has to be that you cannot send information faster than you want. And that's going to give you some interesting constraint on this correlation. For example, you can ask, is there something like a Caron-Huot relation, or Fossil-Weber formula we mentioned earlier, for this correlation function? So this is, and this turned out to be the case, and it's not really useful thing. So I won't go through much of the material of the law, but just to give you some intuition about maybe the most important part. But I think that's a bit subtle when you look at the correlation function. It's what's the correct way to capture dissipation or absorption. And there's actually a simple analogy we could use on pencil, which is that if you study this time order problem, this you can think of as like roughly speaking, measure probability of scatter plus some a component that's really limited. And we can look at its complex conjugate. And if you want to extract the imaginary part of the magnitude, you need a third thing, which is you need to subtract something which is a final polynomial that just measures the probability that say 1 goes to 3 in the absence of 2. And you combine these things, actually the natural object which does that is the square of the probability. That's the interpolation of 1 minus the survival probability. And actually when you start looking at it, because the square has nice properties, it's a positive object, you can bound it. It appears in discussion of chaos. So this is one situation that once you identify the correct object, actually things start to fall in place. You know, you identify the correct object because it has all these nice properties. So yeah, as often the case in physics, the hard step is to guess a formula, but then in this case, once you have a formula, finding the truth was I won't bother reading the full, but was not the hard part. So it turned out that you can claim you can actually reconstruct the full correlation function out of this data, starting from this dissipative part. Construct any operator starting from this object. And this object is much simpler than what because it measures dissipation, it's random parts. Much simpler object, you can use plug into this formula and you construct it. This formula happens to have a property that is analytic in spin. It's crossing, it's an analog of the particle physics formula. So for some quick applications. So one thing it clarifies is that it explains why there's some lot of structure in the spectrum. So this is the scaling dimension of various operators as function of their spin, and the physical operator advantage of spin. And what this formula gives you is it gives you a curve that goes through all of these operators that we can measure, all these different measurements, different angular momentum. And it explains why this curve works down to low spins like J. I want you to understand, so remember I said that at large spin, things essentially decouple. That's why you have this very flat curve with this added dimension. And then we get corrections from interactions that we can understand in terms of exchange of excitations. It's very much in the spirit of particle physics where you understand energy level of object in terms of the say energy level of hydrogen in terms of exchange of photon. There's the same flavor. Here you exchange the scaling dimension of this composite object in terms of things that so it's a way of organizing the spectrum. It explains why our states have to lie one thing it gives you, which we find in the system. And now I want to think that I've been more excited about in recent years, which is the application of these ideas to a completely different class of field theories, of also called holographic. So I realized this is a colloquium, and I was hesitating whether to include the holography. I think it is such a huge part of the theory landscape, particle physics, that it's fair to not to assume that everyone's familiar with it, but it's fair to talk about it. So with the conjecture, signal came out of studying black holes and string theory. But really, at the end of the day, the conjecture has very little to do with string theory. And I just want to give like two little slides, a very down to earth explanation of the phenomenon. So imagine you had a focus one dimensional material that happens to have this holographic. You can put it on the table. Turn something. First thing you do is you shine light. Okay. Imagine that this material has some electric charges. So this material will have some electromagnetic currents that default on powers. If you just look at the material, claims that this is what you would see, is that you would see a shell of energy that extends at the speed of light of this material, probably being more like the Fermi velocity. If you have a material in the material, you'll see the shell extend at the speed of light and extend out the speed. And so this is what you will see. But actually, there's a completely different way of looking at the same physics, where your photon just kept going. And it went under the table, it went into this material, effectively under this table. And just kept going as a point particle. And we claim that this is two equivalent description of the same thing. You can see you have a point particle as a photon in this table, or the shell of energy. The same thing, just a geometrical effect of the space-time that the deeper you go into the dark, the bigger the shell is. They're actually two descriptions of the same thing. And now you test this description. So this is something I had some fun asking this question years ago. And we can test this phenomenon, for example, throwing two photons to the material. Imagine that they meet in the middle. If you have this picture of the ball, then each photon is like a particle, they move in the ball, they hit each other, you have a sharp collision, and you expect like a flash of light coming out of this. That will create a new shell of energy. If you just look at it from the material, this looks crazy. There is two shells of energy that are expanding, all of a sudden there's a new shell found on this image. Really? The whole thing that happens is as the base. It's why if I were to it's really as if the objects that exist on the surface of the table would be inside. Actually, even photons will interact in the extra dimension. Because in the extra dimension, there is a emerging gravity, which is much stronger than our reading gravity. We would actually just look at gravity and see. Of experiment. So if someone could actually have such a material, it would be amazing. You just see that. There's not been a realization now. This is what we will see. I think it's amazing phenomenon. And yeah, so I just want to say a little bit how this goes, how this connects, how we can understand the divergence from the viewpoint of this causality arguments. So first question we can ask is, if I have a model, what kind of model can I put together graphic? It's a rather precise conjecture, but first of all, this has to be a model with boundary. The boundary is this usual theory, it will have to have some relativistic environments. You have to have many degrees of freedom, meaning the stress center two-point function is that. And I also need to have a spectrum that is very sparse, in the sense that all of the measurements, the scaling dimension, all the measurements you can imagine have a large scaling dimension. Take that any model with this property will give rise to this view. That's a conjecture that people made. And this conjecture we could actually nicely address with these two letters 5, because these properties are exactly, they turn out to be exactly what you need to make this commutator square simple. Right? Yeah. The single trace operator turns out that all operators that don't have this property, single trace, double trace are kind of factorized operators. Other operators that don't have this property are killed by the commutator. And other variables that are here, they turn out to give a simple contribution to the formula. So basically, it's exactly the criterion that the inversion formula is easy to evaluate. And once you establish that, you can start establishing a dictionary. So most of it is just kinematics. So it turns out that really all the things that are natural are the boundary, from a field theory language, but all the diagrams we draw on the boundary. So if you ask contribution from the block to the inversion formula, that's exactly extends to the bulk particle. Oxide Caron process in the bulk. Change. All the measurements to the boundary are particles in the bulk. All this dictionary, maybe if you're not familiar with the DSCFT, this dictionary will sound a little bit arbitrary, but this dictionary has been around before. The stress answer maps to the graviton. So if you exchange, if you only can exchange this like the energy bonding answer, then it turns out that this formula gives you exactly what the time gravity can predict. The contribution from the heavy operator is given. If you have a heavy field in the bar, you will normally integrate it out and get the exactly that. And finally, the relative formula in the boundary gives you exactly the transform relation. So nicely mapped. And at the end of the day, showing that you get regenerativity in the bar, just equivalent to showing that you get like ancient gravity is equivalent to showing that the contribution from all the rest is C, which is a problem that you can actually tackle with summarize. So talk about this trap, which leverage self-consistency to solve some theories. Talk about the inversion formula. It's kind of causality statements for this type of correlation functions. And give you an organic principle for the spectrum. And it enables calculation in some strongly coupled. I said some strongly coupled models. I would dream to apply this to QCD. Starting my career, and it's not yet clear whether we can do that, but there are at least some models that we can solve. Maybe I just have 2, 3 more slides. Yeah. So I just want to finish with a few words about all of those. So that's I will be a bit more quantitative here because a lot of it is work in progress. I won't make sharp claims. So we all know a lot about the famous problem how quantum mechanics and gravity fit together in our world. I think a general sharp question we can ask is, well, of course, one expects quantum gravity effects at the Planck length, but we're not going to probe that experimentally anytime soon. But one can ask if it's possible to modify gravity at large distances compared to Einstein gravity. If anything, if some modification makes sense. Broadly, there are it's useful to think of modification in two types. One way to modify gravity is just to say that part of the Newton's potential comes not from exchange of graviton, but comes from exchange of some scalar field. It's called fifth force. And the other way is to really modify engineered reaction by, they say, higher derivative terms or graviton mass. The first type of modification is very mild. It can be constrained experimentally. For example, scalar will behave very differently than spin 2 gravitons. Give you length dependent, but you can measure distance dependence of the force you can measure in kind of like experiment between masses. But theoretically, there's really nothing intelligent I can say about this. This theory is just like consistent and fine. And the other class of theories, when they're not secretly of the first type, it seems that they're actually very hard to achieve without violating causality. That's a relatively new realization that I wanted to highlight. And the argument really fits in the slide, like it was a slide. But approaching from it really has to do with this Caron-Huot relation applied to gravity. Somehow it's not being discussed so much in the past. But the basic point is that you study gravity at low energies, you have just the prediction from Einstein would go like energy square. Plus some, let's say you add some putative higher derivative correction, would grow at energy with another power and some coefficients. You expect this coefficient to be small, with small correction. And remember that Caron-Huot relate low energy stuff to high energy stuff. And the thing that would show up at high energy stuff are positive unknown high energy stuff, the black holes, Einstein stuff, really arbitrary complicated stuff. But what happens is like the imaginary part of this perturbation is positive. So you can write this low energy things in terms of positive unknowns. And actually, you can rearrange the relation to give you basically some rule for Newton's constants and some rules for the modification. And you can actually arrange this some rules, which is something that's a bit uncovered. You can actually arrange some rules that they care only about exotics, higher spin states. One that care about transit-time modes or some things. Really just care about exotics, very exotic particle of state 4. There's no like elementary particle of state 4. It's really exotic. And you can arrange this formula. If you look at this formula, you immediately see that it implies that the corrections to ancient gravity are spread by the mass of these exotics. So there's a big tension between modifying gravity and respecting Carnot's relations. So this is basically the theorem. And to give you a sense of scale, when you put it in numbers, really you have systems that have a kilometer size. You need basically an exotic particle whose mass whose quantum wavelength is a kilometer to be able to see the effect. The other one you can ask, and this is thing that are still debated, I'm not making a strong statement here. We made some arguments in the paper that I'm happy to go to it, especially with people. We made some arguments that actually, if you have such a light exotic, you will not be able to write it. String theory, as soon as you have exotics that couple to gravity, you also have exotic string quarks that couple strongly to. So, jury is still out on this argument, I'm still working on improving it. People have made similar arguments about gravitational mass. It's really being argued to basically require exotics that are so light that the theory does not make sense. That's the theory. So we've been progress on very narrowing down what modification of gravity makes sense and which one will violate causality as we expect. So I'll stop here. Conclusion. Try to find some implication of this notion of relativistic causality that singulars can go faster than quantum. And it's a useful tool it explains many features in our world, but it's also a useful tool to perform calculations. Good.
We have a few minutes for questions. We have to leave the room about 10 minutes or so. Before I take questions, I just wanted to say the normal reception right outside is not happening right outside today. There's from the Diversity and Climate Committee and Red 5 are hosting something on the third floor, so we can go there instead outside. Okay, okay.
So the questions about booster.
Yeah,
Two questions.
okay.
That was about booster. You said that you use the standard equation for 3 dimensions 2 plus 1, and then you said that we use Kazan.
Yeah.
Is there any practical purpose of this? Is there any practical advantage of doing this?
That's a good question. So this means you try to essentially this give you different type of here we're going to look at the stair extension or square configuration. And this gives you a completely different set of constraints. When people combine those type of constraints together, you do find faster. So that
And if I may, don't take it with any negative side. Question about where bootstrap approaches generally go. You start getting exponents with higher and higher accuracy, which probably will never be seen and there will never be seen in experiments. And at the same time, you don't get exact numbers, you still get approximate numbers. So where's the whole approach goes? Do you go making exponents more and more precise without any way to check this in any real experiments? Or is there something more than this?
people actually make experiments where you see the space station. And you use the fact that we can have a very good expression there, so there the exponents there. So actually there are some situations where this actually exceeds. But for the most part, I agree that I think in my view the useful direction for this to go is to look at the theory of strong force. Never find the scale. It's recording function that have a scale of them. But I think that the way to transform it.
Any other questions? Jen?
To your question, one is in the beginning here you mentioned about probably using an elasticity feature to then you mentioned about something about marrying the phase of amplitude. I assume what you meant is I want to confirm that you meant how additional phase dependence of the energy scale involves because we cannot measure the phase of understanding physics.
Yeah, absolutely. Yeah. You have to set some reference somewhere. So what would it be by so mathematically, I think it is in the precise statements that actually quantum mechanics, if you take a state, the compare with this context conjugate, there actually is a way. Observables. There's an explanation of organic. If you're below, there's an absolute down to the so there's an absolute place where we will use.
Yeah, even below threshold, I understand, shouldn't be to Israel, all of observables invariant and refacing. So I think what you meant is I measure the additional phase development when I go from threshold. So that's the functional dependence of amplitude upon energy scales. I think that's what you meant.
I think the point is that there's natural there's a question called CPT that gives you a natural motion which will be the coefficient. CPT breaks this reflecting the Then the phases will be fine. Awesome.
There's a lot of information there in this talk. I understand we cannot go back in time and see it again, but I think it's the point. Let's thank our speaker again.
It's up to you if you want to join that reception. Oh, sure.